Why, just because a passenger had a better cabin or embarked on a different port, would they have higher probability of survival? This helps us understand why a specific prediction is high or low in a very intuitive way. Let's be real, nobody wants to face legal consequences. If you will not convince previous two groups, then you will not arrive at this third step. But this is the most crucial one. It is always better to be safe than sorry. Hello everyone, my name is Jakub Cieślak and I'm a senior data scientist at Tips AI. And today's deep talk will be about explainable AI, and it's a with interrogation detective style subtitle if you allow. What your tree-based model is hiding from you and how to make it talk. And you may ask, why talk about it? Well, in my opinion, explainability is the easiest way to gain trust in your model from your stakeholders and product teams. But also, it is a tool that enables transparency and accountability during model development, and these terms are becoming more and more essential every day, with AI-related regulations being implemented across the world. And you might now wonder, what will we cover here in this deep talk? So, first, we will talk about what is explainable AI and how different approaches work. How can we explain our predictions? Here we will see how SHAP values and partial dependence plots can help us see what our model sees. Then in why should we explain our predictions, I will talk about different perspectives on why explainability should be an essential part of every machine learning project. And finally, common mistakes and recommendations. A quick summary of do's and don'ts. Let's begin. What is explainable AI? So, let's say we have a trained model and a set of features that go into it. We receive a prediction, but sometimes we will ask ourselves how this particular set of features results in this particular prediction. What would happen if we would change some of these features? So, methods of explainable AI try to answer exactly these kinds of questions. They help study how we can decompose our predictions feature by feature, but also give us insights on general tendencies of the model. Here, we have tabular examples, but we can also apply XAI to other types of ML tasks, such as computer vision, where we can see what model sees, or natural language processing, where we can observe how models understand written words. Regardless of type of the problem that we have to solve, there are two main distinctions of XAI methods. We have local explanations that zoom in on a single prediction. They explain why this particular input received this particular output and which features pushed the prediction up or down. On the other hand, we have global explanations. They help us understand how the model behaves overall, and they are looking at the big picture. They answer questions like which features matter the most, what patterns the model has learned during its training. And both are important, but they answer different questions. Local explanations help with individual decisions, debugging, and accountability, while global explanations help with trust, governance, and validation. Okay, so we now know that, and let's go into how can we explain our predictions. And before we begin, there will be a quick disclaimer. So, throughout this chapter, while showcasing XAI methods, I will be using a Python library that is called SHAP, and it's a good go-to library for explainable AI, especially with tree-based models. And for the dataset, we will use a classical Titanic disaster dataset. Okay, so let's dive right in. As before, we will go through local and global views. Here we have SHAP values, and mentally, you can think of each SHAP value as a small nudge that pushes the model prediction higher or lower. Usually, it takes long to compute SHAP values for general methods, but because we have currently tree-based models, we have a specific algorithm called tree-SHAP that takes advantage of tree structures of the models and it speeds up the computation. It still isn't that fast, but it is faster than the usual approach. So, going back to the plot. Locally, for a single passenger, the breakdown plot shows us each feature's contribution step by step. It starts from average survival probability that it learned during the training, that is in the bottom, and adds or subtracts the effect of each feature until we arrive at predicted passengers' survival at the top. This helps us understand why a specific prediction is high or low in a very intuitive way. And globally, a SHAP summary plot will tell us which features generally drive predictions across all passengers, and whether high or low values that are annotated on this plot on color scale from blue to red increase or decrease survival probability. And as for the other method, still local and global explanation split, for local view, we have individual conditional expectation. In short, ICE. Here we take a single passenger and see what the prediction would be if this passenger had a different class assigned to him. So we wonder if we had a different passenger that would have all other features equal to this passenger but had a different passenger class assigned to him, what the prediction would be for that passenger. And for global view, we have partial dependence plot. It shows global and average effect of a feature across all passengers. It answers the question, on average, how does changing passengers' class, age, or gender impact survival predictions? So we really quickly went through really powerful methods and how they work. Now, let's talk a little bit about why should we explain our predictions. And the thing is, it is actually really hard to pinpoint one main reason why someone would want to claim predictions of his model. And because of that, I decided to approach the question from three different perspectives. First one is technical, debugging and model quality. XAI is useful even at the earliest stages of a project, where it can help us debug how model trains and if its decisions make sense. So let's get a closer look. As we know from our experience, there is much more to how good model is than just how its metrics look like. By knowing predictions, by knowing how predictions are constructed, we can detect issues like data leaks, for example, where model learns from information that wouldn't be available at the time of prediction. And the other one, hidden bias that can lead to unfair decisions. Example of that can be a loan acceptance model that has started to use zip codes for its predictions. And zip code, as we know, should be irrelevant from a decision-making standpoint. It just informs us of the address of the client. But model uses it as a proxy to find lower income neighborhoods, leading to unfairness. And there are many more examples of these behaviors, and there is one common thing amongst them: inflation of the metrics. So we have really, seemingly really good models that will not perform that good in the production setting as we see it behaving on validation sets. And explainability and methods of explainable AI are essential to prevent that from happening by allowing us to detect them early enough. The second one, trust and adoption. And this one, in my opinion, is really important because every product has to be, like every good product has to be trustworthy. And it's hard to gain trust with only numbers. If we fail to gain trust in the first place, there will be no adoption of our model. So, when talking about trust, there are usually three groups of people that you will have to convince that your model is worth using. The first one is you and your data science team. Here, amongst the people that deal with models every day, you can limit yourself into talking about ML metrics, hyperparameters, and best features. Second is stakeholders. Here you will use KPI metrics and cost reducing effectiveness on a big picture. And the third one is a product team, and you are creating a model for them. These are the experts that have been doing what you are trying to accomplish by building a model for years. They have the business knowledge, they have the experience and intuition. And don't get me wrong here, if you will not convince previous two groups, then you will not arrive at this third step. But this is the most crucial one. Because the product team will not care about shiny ML metrics. They will not care about the cost reducing effectiveness. They will want to know why a model behaves that way. Why a prediction for something they have intuition for is different than what they believe it should be. Because they will not trust the black box if it's counterintuitive for them. And without trust, there will be no adoption. To put simply, model will not be used. And with that being said, let's proceed to the last point, which is also really important, and it is legal and ethical risks. So let's be real, nobody wants to face legal consequences. And because there are many regulations that force us to explain predictions of our model to the clients, XAI is mandatory in these cases. And from ethical side, we also share a common responsibility to make our models fair, and as it will impact the lives of other people. So, with legal, there is a lot of movement around regulating development of artificial intelligence in the past couple of years. Each year, there are more and more regulations passed throughout the world. We have EU's GDPR right to explanation, EU AI Act, UK's GDPR and Data Protection Act, and obviously others. And these regulations state that upon request from the client, vendors of automatic decision systems, and in our case, machine learning models, have to provide meaningful explanation about decision made by a system. Also, some of them even require that a given client has to have an option to request a human review, so bypassing our decision model completely. And from ethical standpoint, we do have influence over major events in people's lives. Mortgages, car loans, hiring and HR processes, healthcare, and others. These models aren't always about ROI or KPI metrics. Fairness and transparency matter just as much when predictions impact people's lives. And explaining predictions will enable us to detect unfairness issues, but you have to remember they are not used to solve them. So, the last chapter, common mistakes and recommendations. I would like to focus on common mistake number one, which is really crucial. It's the most common mistakes of all when it comes to XAI, and it's also the most destructive one because it drives a lot of business decisions that involve earnings, and this is really misleading. And if I had to choose only one thing that you would remember from this whole talk, I'd like you to remember this. So, to start, let me go back for a little bit to an example that we saw at the beginning. We have our local and global explanations. We look at the features and see that gender and age are really strong predictors. And just to remind you, we are trying to predict the probability of someone surviving through a Titanic disaster. And since we actually know how Titanic evacuation was performed, and we know that women and children had a priority on embarking on lifeboats, it makes it very natural for these features to influence probability of survival, whether someone is a man or a woman, or how old is he or she. It has a direct influence on probability of survival. But as we look at passenger class and embarked, so on which port someone embarked on, we are struck with the question, why, just because a passenger had a better cabin or embarked on a different port, would they have higher probability of survival? And since this dataset was studied extensively, we know the real cause. The passenger class and embarked are just proxy variables. They are used because of correlation to a location of someone's cabin on Titanic ship. And actually, to be precise, not only location of someone's cabin, but a distance that had to be traveled to reach a lifeboat. So it really matters during a disaster. And that distance to, to be traveled to reach a lifeboat is the true difference between life and death on Titanic. Not money paid or port someone started their travel with. And this is generally true for most of modern models because they are so good at predicting the outcomes because they find these unintuitive and entangled interactions between features that normally humans do not see. And by doing that, they approximate what isn't available in the data. But also because they do that, they give a false evidence of causality. So please remember that just because something is an important feature for predicting the outcome doesn't mean it is a part of what has caused it. So, uh, we will go through common mistakes, and we will go through five recommendations from us. And we already went through first common mistake, which was feature importance can be misinterpreted as causation. Don't let it fool you. We warn you, this will happen. This is really tempting to say that some feature, which is a number one predictor in our model, is a number one cause of a situation. Same one, local explanations will sometimes contradict general trends. So just because something shows on a local explanation plot doesn't mean it will show up everywhere. SHAP values can be unstable for highly correlated features. This is something that we didn't talk about, but it's really essential to remember when using SHAP values. Partial dependence plots can be misleading if features are highly dependent. So let's take an example that we covered previously. When we change someone's passenger class from third to first, it is obvious that the price of the ticket should also change. We know that first class tickets are much more expensive than third class tickets, but partial dependence plot assumes that no other feature changes its value. So it in that term is wrong because you cannot buy a third class ticket for the same price as the first class ticket. The fifth one, explanation complexity can overwhelm non-technical stakeholders. Actually, sometimes even technical ones. And if you are overwhelmed already, then I'm really sorry. Okay, now let's go through recommendations. Number one, contextualize explanations with domain knowledge or subject matter experts. And it's really simple. Always check what you find with what you know. And if you know nothing about the subject, ask someone who does. Number two, always document findings, weird interactions, and biases. You will not remember what you find a couple of months ago, and you will have to know that because you will have to compare new results with previous ones. Number three, regularly recompute explanations when the model or data changes. It's directly connected to number two. Number four, use XAI to detect data leaks and biases. XAI methods are ideal for these kinds of things, and no one wants them in their model. And final, number five, compare multiple explanation methods to validate insights, because it is always better to be safe than sorry. And with that, thank you very much for your time. And if you like this content, please like and subscribe.